Hello and welcome to today's video. So in today's video we are going to be considering this question just to explain the concept of strain energy and basically stress strain relationships. So let's consider the question. The question says a rod 1 meters long is 10 centimeters squared in area of a portion of its length and 5 centimeters squared in area for the remainder. The strain energy for the step bar is 40% of that of a bar 10 centimeters in area, 1 meters long under the same maximum stress. What is the length of the portion of 10 centimeters squared in area? Okay, so we are basically going to draw a diagram to properly explain this question. But before that, let's pick out our parameters. We are given that a rod 1 meters long, so which means the length of the rod itself, okay, length of rod L is actually 1 meters, and it says is 10 centimeters squared in area at one portion. So let's simply use first area or area 1, call that A1 to be equal to 10 centimeters squared and 5 centimeter in area for the remainder. Okay, so area 2 simply A2 is 5 centimeters squared. Alright, so it was stated that the strain energy for the step bar is 40% of that of a bar 10 centimeters squared in area, and we know that it is simply the first area that has 10 centimeters squared in area. So they are simply saying that the strain energy of the second bar is 40% of that of the first bar. So you simply have strain energy condition, okay. The strain energy of the step up bar is 40% of that of the 10 centimeter squared area. So we know that the 10 centimeter squared area is what? The first portion, A1. Therefore, this simply means that the strain energy of bar 2 is equal to 40% of that of bar 1. So that simply implies that U2 is equal to 40% of U1. So this simply means that U2 is equal to 40% simply means 40 divided by 100, which is around 0.04 U1. Sorry, which is around 0.4 U1, please. Which is around 0.4 U1. Simply 40 divided by 100, which is around 0.4 U1. So the strain condition, strain energy at portion 2 equals 0.4 strain energy at portion 1. Now let's draw a diagram to illustrate this whole thing. We have a bar. The first area is 10 centimeters squared and the second area is 5 centimeters squared. So if the area of the first portion is 10 centimeter, it means the first portion has a bigger area or a bigger diameter than the second portion. So you have something like this. Okay, you have something like this. Alright, so this is what a vivid example of what the question is saying looks like. So this is the first area, A1, the second area, A2. Okay, now the length of this bar was given as what? 1 meters. Now we don't know the length of the first portion, L1 unknown, length of the second portion also unknown, L2 also unknown, and the question is asking us to find the length of the 10 centimeter squared area. Remember, the first portion is a 10 centimeter squared, here has area of 10 centimeter squared, and the second portion has area of 5 centimeter squared. So they are simply asking us to find the first length, L1. Okay, so having these conditions in mind, we were also given strain energy of the second strain energy, U2 was given as 0.4 U1. So this is basically what the diagram looks like. Since we weren't given the first length, we are asked to find length L1, length at the 10 centimeter area portion. So L1 is unknown. That's what we're asked to find. But then If the total length of the bar is 1 meters, it simply means we can find the length of what? The L2, or the length of the second portion of the bar, with respect to the first bar, or with respect to the length of the first bar. So this means that L2 will be equal to, if the entire length is 1 meter, then it means L2 will be equal to 1 minus L1. Also keep this condition aside. So let's start our analysis now. First thing to keep in mind is, what is strain energy? What is strain energy? Okay, so now let's find out what then is strain energy. Okay, what then is strain energy? Strain energy mathematically is given as force times change in length all over 2. Okay, there are lots of formulas for strain energy, but the base formula is simply this: force times change in length all over 2. Now, how do we relate this? We are going to be doing a little bit derivation to obtain a formula to calculate this. You know that mathematically change in length relates with Young's modulus and stress according to the formula length times force over area multiplying Young's modulus. This is the formula for change in length, relating stress to Young's modulus, or simply force, area, and Young's modulus together. Okay, so putting this into this equation, you're going to find out that strain energy U is equal to, we said you have force, so you have force times change in length, and change in length is simply this: length times force over, remember there's 2 here, so 2 times area times Young's modulus, and you have this. Okay, so this is going to now be equal to, remember, force times force gives us force squared times length all over 2 times area times Young's modulus. So this is the formula for strain energy. Now, remember, in the question, it says the stress are the same. Okay, one of the conditions in the question says the stress are the same. Let me read through the question once again. So once more, the question says the strain energy for the step bar is 40% of that of a bar 10 centimeters squared in area, 1 meters long, under the same maximum stress. So under the same maximum stress simply implies that, okay, under the same maximum stress simply implies that stress 1, sigma 1, is equal to stress 2, sigma 2, since we have two portions of the bar. So the first stress is equal to the second stress, keeping that condition in mind. Now let's move on to our analysis. So if we have this to be the formula for strain energy, then this simply implies that the first strain energy, okay, U1, is going to now be what? The first force F1 all squared multiplied by length, or the first length, all over 2 times the first area A1 multiplied by Young's modulus. But Young's modulus is actually a constant, so it doesn't change. But then, what is force? Recall again that force is simply what? Stress times area. So this simply means force 1 becomes stress 1 times area 1. Now let's put that into this equation. That simply implies that the strain energy 1 is going to now be equal to, we have force 1 squared, and force 1 is stress 1 times area 1. So force 1 squared simply becomes stress 1 squared, area 1 squared multiplied by length 1, all over, we have 2 times area 1 times Young's modulus. So from here, area 1 cancels one of this area. That simply implies that our strain energy for the first bar is simply what? Stress 1 squared multiplied by area 1 is left now, 1 here is left, multiplied by length 1, all over 2 times Young's modulus. So this is the strain energy which we are going to be using to carry out this calculation. So this is for the first bar. It means for the second bar, this simply means for the second bar, strain 2, which is U2, is going to also be what? Stress 2, the strain energy, sorry, okay, is going to be stress 2 times area 2 times length 2, all over 2 times Young's modulus. Young's modulus is a constant parameter. Okay, so I'm flipping over now, but before flipping over, not forgetting, it was stated that the strain energy in the first bar or the strain energy in the second bar over here. Okay, it was stated that the strain energy in the second bar is 0.4 times the strain energy in the first bar. So keeping all of this in mind, keeping this formula as well in mind, these formulas as well in mind, let's flip over now and start our calculation. So let's rewrite our formula a bit. We said U1 was obtained simply as stress 1 squared times A1 times length 1 all over 2 times Young's modulus, and U2 was obtained as stress 2 squared times A2 times length 2 all over 2 times Young's modulus. And if it was stated, recall that U2 is 0.4 U1, that simply means that the whole of this is 0.4 of this of the whole of this. That simply means that the whole of this is 0.4 of the whole of this, which means mathematically stress 2 squared times A2 times L2 all over 2 times Young's modulus is equal to 0.4 U1, which is 0.4 multiplying everything here. So we have stress 1 squared area 1 times L1 all over 2 times Young's modulus. Now, we have all these conditions in mind. Not forgetting, earlier I said in the question, it is stated that they all have the same stress. So if they have the same stress, that simply means for equal stress condition, stress 1 is equal to stress 2. So which means this also implies that stress 1 squared will also be equal to what? Stress 2 squared. So if the stresses are the same, then let's look at this relationship once more. If the stresses are the same, it simply means that stress 2 squared will strike stress 2 squared. Sorry, stress 2 squared will strike stress 2 squared out. This is 0.4. Okay, again, 2 will strike 2 off here. Young's modulus is constant. They will also clear off. So which means I am left with area 2 times length 2 equals 0.4 area 1 times length 1, which is what I am left with. So the remainder of this equation now from those conditions means area 2 times length 2 equals 0.4 area 1 times length 1. Okay, but not forgetting, we said earlier that length, let's pull it out again. So not forgetting, we obtained earlier that if the total length of the rod is 1 meters, and okay, we call the first portion length 1 and the second portion length 2, that length 2 can be found in terms of length 1 since total length of the rod is 1 meters. So length 2 is simply 1 minus L1. So in place of length 2, we are simply going to be using 1 minus L1 to represent the length of the second portion of the bar. Okay, let's flip over now. Alright, so having that in mind, we have here, so L2 is equal to 1 minus L1. That means in place of this equation, this becomes A2 into 1 minus L1, and that's equal to 0.4 A1 L1. Now let's put in their actual values. The area of the second portion was given as 5 centimeters squared, and the area of the first portion was given as 10 centimeters squared. Now, mind you, there is no need to convert since both areas are in the same unit. Okay, they will obviously cancel out. So you have area of the second portion, which is 5, multiplying 1 minus L1, and this is equal to 0.4 times area of the second portion was given as 10 times L1. So if we expand this bracket, 5 times 1 gives us 5 minus, okay, 5 times L1 gives us 5 L1, and this is equal to 0.4 times 10 gives us 4 L1. So at this point, you simply collect like them, send minus 5 L1 over here. This simply implies that 5 is equal to, if negative sign cross this equal to sign, it becomes positive. So I have 4 L1 plus 5 L1. So this simply implies that 5 is equal to 4 plus 5 here gives us 9L1. Hence, to find the first length, this implies that L1 is equal to 5 all over 9. So this simply implies that length 1 is simply equal to, let's obtain 5 divided by 9. That gives us 0.56, 0 point, or approximately 0.6 meters. So which means the length of the first portion is 0.6. And if this is 0.6, which is what this question is asking us, the length of the portion of 10 centimeter squared area, that's simply 0.6. And remember, L2, we obtain L2 to be equal to 1 minus L1. So this simply implies that the second length, or the length of the second portion becomes what? 1 minus 0.6. And therefore, L2 is simply equal to 0.4 meters. Alright guys, so that's it. This is the answer to the question, but then additionally you can further to obtain this. That's it on that question. I will see you in the next video with another question. Thanks and cheers.